what's going on, guys? Welcome back to Farcon Technologies, and in this video we'll be discussing something that's called Ipv6 Slaac. What is it? What is it about? I have no clue. No, I'm just kidding. But no, I have gone ahead and made a presentation here on Ipv6 Slaac. So let's get straight into this. So Ipv6 Slaac. Slaac stands for Stateless Address Auto Configuration. Okay, let's move on here. What is Slaac, right? What is it? Why is it even called Slaac? I mean, obviously we found out why it's called Slaac from the previous slide here. It stands for Stateless Address Auto Configuration, but what is it? What is it used for? So Slaac is used. I misspelled the word, but it's okay. Slaac is used by host devices, right, to dynamically learn their IPv6 addresses. However, it's not really learn, right? It's not like DHCP learn. It's a bit different, and I'll show you how it works. So it brings me over to my next slide. How does it work? A host, right? Let's take a PC. It connects to the network, right? Then that same host solicits the router by sending a message to all routers, Multicast, which happens to be FF02, : 2, and it basically asks, hey, what's going on? Are there any routers? Respond to me. Are there any routers on the network? And router, what the router does, it sends back a router advertisement, also known as a shortened version of RA. And that router advertisement contains a lot of good stuff. And I'm actually going to go ahead and link a video in my description of Keith Barker. He goes in really good details about Slaac, so make sure that you go check that out. This is a bit like a quick introduction to Slaac type of thing, yeah? Okay, so as I was saying, this router advertisement will have a network prefix, aka subnet ID, needed for the host to create its IPv6 address, right? So, and the host uses EUI64 process, which, by the way, you can check out on my previous video that I did. It uses the EUI64 process to create the interface ID, right? And adds it to the prefix obtained earlier. So it adds the created interface ID to the prefix learned through router advertisements, right? And then it goes through the process of a duplicate address detection, just to make sure that it doesn't have the same address as anybody else on the network. All right, so I'm actually gonna go ahead and quickly demonstrate it to y'all on Packet Tracer. Yay! All right, let's get into this. Let's actually go ahead and let's go ahead and see if there is any IPv6 addresses enabled. So show IPv6 interface brief. There is none. Okay, so let's go ahead and enable it. This IPv6, this host is connected to the router on interface G00. Okay, so we'll go ahead and configure that interface. Interface G00 IPv6 address. Let's do 2001 DB8 1 1 That's our IP address. That is our IPv6 address right here. All right, cool, no problem. Let's go ahead and check it out. Do show IPv6 interface brief. Okay, so this is our IPv6 address, right? This is our link local. Something that I actually wanted to show you is not this. So let me go ahead and show IPv6. Let's do this. Show IPv6 what's going on? Interface. There we go. G00. Okay. Alright, as you can see here, it's joined this group right here, right? Oh, almost forgot here. Let's do a check. Okay, perfect. Let's go back and let's do this command again. Okay, cool. So it is joined to ff02::1 multicast, which is everyone, right, who runs IPv6 addresses. But as you can see, it hasn't joined the ff02::2, which is for all routers, and that is because we haven't enabled IPv6 unicast routing, and this is actually something that I also learned from Keith Barker, so make sure that you go ahead and check his video out. The video link is going to be down in the description. So let's go ahead and config t, and then let's go ahead and enable unicast routing, and then go back, and then what we will see is, yes, there we go, it's joined all router multicast address. Okay, so now we have configured everything here. The prefix is configured, the IPv6 itself, the address itself on the interface is obviously configured. So let's go ahead and use Slaac on the host to obtain our IP address, IPv6 address actually. Let's see, I think it's fast Ethernet. Hold up. Wait, what's going on? Automatic. Okay, yeah. Oh, right. Okay, never mind. Okay, here we go. So you change this configuration to automatic, which causes it to use Slaac, right? And as you can see here, for the interface ID, it did use the EUI64 process, which used this MAC address right here, right? And it created the interface ID for the prefix. It took the prefix of the router that it's, the interface of the router that it's connected to, which is G00, and from what we remember, this was the prefix. Okay, all right. So now let's go ahead and what I actually want to do, I want to change it to simulation, and I want to go through this process right here. Let's see. So Slaac uses NDP, Network Discovery Protocol, which is literally just ARP for IPv4. So if we read here, NDP process sends a router solicitation message, just like I mentioned in my PowerPoint. The source IP is not specified. The device says it's to port's IP address. Okay, which in our case is the link local address of our host. The device says the TTL in the packet, obviously. The destination IP is in the same subnet. The destination IP is, as you can see, FF02, just like I mentioned in my PowerPoint. The next hop byte is the multicast address. The ND process sets the frame destination MAC address to a multicast MAC address, this one right here, and the device encapsulates the PDU into an Ethernet frame, and it sends out the frame. Let's see what happened next. Router, hold up, let's go one by one. Okay, so the router receives the frame here. The frame's destination MAC address matches the receiving port's MAC address because it's a multicast address, right? The device decapsulates the PDU from the Ethernet frame. As you can see here, it says the packet is coming from an outside network. It recognizes it as an outside network because we are sending it to the multicast address, but the source IP address is FE80, which is, I mean, it's literally not the same address. It's not the same prefix as this one, so it recognizes it as an outside address, okay? Outside network. The destination IP address is a multicast, obviously. The device dispatches the packet into the upper layer, so pretty much they see the packet as it sees the packet as an ICMP packet, so it processes the packet, and then the packet is an NDP packet because we're discovering the neighbor, processes the packet, receives a router solicitation message. Okay, that's crucial. Let's actually look this up. Let's see, let's check this out here. I have not looked into this yet. So, yeah, router solicitation message right here. You see source, destination. Perfect. Okay, going back to our outside model. Okay, and that is it. Let's see. So obviously the router sends back a router advertisement. The router advertisement, this is actually very crucial. That's also something that I learned from Keith Barker's video. He was showing the Wireshark captures, and the message type for the message code or message type for router advertisement is 134. So let's go ahead and see what it's saying here. Obviously it says the MTU, and as you can see here, it sends the prefix, right? So the subnet ID of that of the network that the interface is connected to our host to use for its IPv6 address. Okay. Oh, sorry about that. As you can see, it sends it back to everyone who is speaking IPv6, right? So obviously, and then it just sends it out. Sends it to the PC, the PC receives it, constructs a neighbor solicitation for the target IPv6 address. Wait, what's going let's look at this one first right here. From the destination MAC address matches the receiving port's MAC address. Okay, obviously since we send it to the multicast of everyone who speaks IPv6, the device decapsulates the PDU Ethernet frame. The packet's destination IP address matches, obviously. The packet is an ICMP packet, okay. The packet is NZP packet, okay, yeah. And then receives the advertisement message. Okay. NZP process constructs a neighbor solicitation for the target IPv6 address. Let's see here, what's the source? Okay, so it constructed the IPv6 already, the PC, right? And it's sending it to, okay, it's sending it to the solicited node multicast address. The device says it's its destination IP address in the same subnet. The device sets the next hop to destination. The next hop IP address is a multicast address. So this is something actually that's interesting. So now I guess this is the part that I was speaking about, because I haven't actually seen this before, right? Because I'm also new to this. So I guess this is where, right, it's going through this process right here, the duplicate address detection. And the reason why I'm saying that is because it's sending a router solicitation, neighbor solicitation for the target IPv6 address, which is FF02::1, FF3, FFC3, DC99, and if you notice it, this is the last 6 hex digits of our source IP address. And this prefix right here, the first 104 bits, FF02::1, FF, that is actually prefix for the solicited node multicast address, which is used for, from just going off of my knowledge, it's used for MAC discovery in IPv6. So I'm guessing, we're gonna look to this together, and I'm sure that it's doing the duplicate address detection. So it sends it to router 0, receives the frame, destination MAC address matches the receiving port's MAC address, okay. The broadcast or multicast address, okay, cool. The device decapsulates the PDU, okay. The packet is coming from an outside network, okay. The device looks up a NAT table for the necessary translation. Is a broadcast or multicast? The device dispatches the packet to the upper layer. ICMP, NDP as a neighbor solicitation. The neighbor solicitation's target IPv6 address does not match the receiving port's IPv6 address. The source IPv6 address is in the neighboring table. The device updates the neighbor table with the received information. So, hold up. So the neighboring solicitation target IPv6 address does not match the receiving port's IP. Obviously, yes. The source IPv6 address is in the neighboring table. So it is in the neighboring table, right? The device updates the neighbor table with the received information. Okay. The NZP process drops the packet. Alright. And I guess that is it. And that is something different. Yeah, this has to do something with the routing. Obviously, let's see what it's saying here for MVP. And yes, so at this point they're just exchanging the NDP info. Nothing too specific, to be fair. Yeah, I mean, it's pretty much all the same things, same old, same old. Yeah, same old things. Yep, and yeah. Well, our main focus here was that this is how Slack is used, pretty much. And yeah, I guess this is a wrap for this video. Again, I will be linking Keith Barker's video, which goes into some really nice details about Slack and about a little bit of DHCP version 6 as well, that can be used with Slack. Here I just wanted to do a bit of a brief overview of Slack and just kind of show you what the PC does, you know, when it's configured to use Slack to dynamically learn the prefix of the Ipv6 network that it's connected to, and then use the EOI64 process to create its own IP address. Yeah, this is it for this video. Please, if you don't mind, go ahead and subscribe. If you enjoyed this video, go ahead and like the video. If you didn't like the video, if you didn't find it useful, you can go ahead and dislike it. Don't worry, it's fine. You're not gonna hurt my feelings, man. Come on. But other than that, peace be upon you all, and till next time.